we were looking at the physics, we looked at the physics of X-ray scattering, starting with just a single electron, a free electron stationary at rest, an electron bound in an atom, and considered the case, we considered the cases, or in the second instance, considered the case where the frequency omega of the X-rays greatly exceeds any natural frequency for the dipole nucleus electron dipole oscillator. So, and we remember that in the dipole oscillation, the nucleus moves so little because it's so much heavier than the electron that effectively we're looking at just electron oscillation. And what do we mean by the natural frequency? If you remember from school physics when you looked at things like a pendulum or a weight on a spring, the natural frequency is, so consider the case of a weight on a spring. You pull down the weight and then let it go, and it begins to oscillate. And it reaches a kind of equilibrium frequency where with no other pulling on the spring or no other disturbance of the system, spring and weight, that it has a natural oscillation frequency. Just like a pendulum in a clock has a natural oscillation frequency. Now those motions can be damped, of course, by friction, by whatever, but we're considering ideal frictionless case for the moment. So then we went on further and considered the basic physics of the scattering when the electron is in an atom such that the natural frequency of dipole oscillation is approximately equal to the frequency of the X-rays. Now, what kind of an electron could have a natural frequency that matches X-ray frequency? So if we consider 1 angstrom wavelength, like the X-rays, the corresponding frequency, if you calculate with the Planck-Einstein relationships, is h nu and so on, is 18.8. I remember this number. I don't know why. 18.8 times 10 to the 18th hertz. So 18.8 times 10 to the 18th motions per second, oscillatory motions per second. So that's attohertz. Well, if it's going to be an electron that is in that energy range, it has to be quite a high energy electron. So this would be an inner electron close to the nucleus. When the electrons that are in those shells, the K shell, for example, they have very high kinetic energy in their motions around the nucleus. The electrons farther out in the valence shell, L or whatever valence shell you're considering, they have less kinetic energy. Right? They correspond to lower frequencies, softer frequencies. So when we are considering the case of scattering by an electron with a natural frequency that approximates the X-ray frequency, we get into this realm of anomalous scattering. And then that's all the case of considering just one electron at a time. We can consider next a many electron atom, a polyelectron atom, and then we could consider polyatomic molecules, and then orderly arrangement in a lattice of molecules, and then finally a crystal structure. So this is the kind of hierarchy of X-ray scattering by matter. So we looked at some of that. So we have the Thomson result about the electric component of the scattered radiation is given by this relationship to the acceleration, and the direction of things depends on the direction of this observational vector. So we're out here at some point in space. which is a position vector r away from the oscillating charge. So there's the Thomson result in scalar form, and here it is in vector form. Okay? The way we get to A sine of alpha is by considering first the cross product of this unit vector. When we put a little hat on top, we imply a unit vector. That is, this position vector, however long it might be, divided by its length. So here we have a length and direction, and here we have just length. So now we get a direction, a unit direction vector, r hat. So if we make a cross product of r hat with the acceleration vector, okay, take that result, and then the result of that cross product with the direction vector again, we get the component of the acceleration that is perpendicular to the direction of observation. Okay? That's what all that's about. So that's an entirely classical result, just thinking about point charges and electric force interactions, Coulombic interactions. Okay, that's just. So here's Thomson's result. We have to balance this Coulombic electric driving force, which is the electric component of the incident X-ray wave. For the most part, we're ignoring anything about the magnetic component of electromagnetic radiation in connection with the interaction with electrons. So it's the electric component of the oscillating electric field that is part of the incoming X radiation, and then the motion of the electron that results from the imposition of this force has to follow Newton's law of motion. We're talking about classical circumstances here, not relativistic or quantum conditions. Okay, so those two forces must balance, must equal. So MA equal QE. Q is the charge of the particle, in this case an electron. So there's the electron charge. Q is equal to the negative E. When we write the E this way for an electron, that's the amount of charge on the electron. It could be positive or negative, for example. A hydrogen nucleus has a charge of plus E, right? 1 unit, where we're counting, charge in units of electrons. Okay, so the negative charge on the electron, this oscillating electric field of the incoming radiation. So we solve that little equation for the acceleration that the electron experiences under the influence of this force. Okay, so we have the acceleration here. We just call this lump of constants in the front minus E naught over mass of the electron, m sub E. Just call that a collection of constants, A naught. There. So that now goes into, that result for the acceleration goes into the Thomson formula for the scattered, the electric component of the scattered radiation observed at some point at a vector distance r away from the nucleus. Okay? So we have this result from the Thomson analysis. So that the amplitude of this outgoing electromagnetic radiation is given by this ratio of the charge on the electron, the square of the velocity of light, the distance away of the observer, and this collection of constants that we call A naught here. So making all those substitutions, what we come down to is this result, where what we have done is replace, okay, so we put in there the negative of the electron charge, the mass of the electron, collect those constants together out front, okay? This collection of constants is called the Thomson scattering length of the electron. Right? So this represents then the electric component, the amplitude of the electric component of the scattered wave. And we symbolize this collection of constants by the R sub E, the classical electron radius. I'm going through this again because I had the feeling that I rushed through it when we met last time, and it does require a bit of thinking to just digest these basic physics phenomena that are going on with electromagnetic radiation scattering by an electron. So this just summarizes the result. We call this collection of constants E squared over mc squared the Thomson scattering length of the electron, and then it multiplying the electric component of the incoming radiation and dividing by the radius to the distance to the observation point gives us the amplitude E naught of the scattered radiation. So here we're talking about the electric wave, E naught e to the I omega t, but that amplitude is just the prefactor of the imaginary exponential factor. And then this shows that that thing that we've been calling, that we started calling the Thomson scattering length for the electron, is in fact a length, if we take this result and plug in for these constants, just their dimensions, so it's a square of charge divided by a mass times the square of a velocity. Go through all of this just dimensional analysis, we come up with a distance. So we call that then, we name that distance the Thomson scattering length, or the classical electron radius. And I think we mentioned last time that in terms of thinking of the radius of an electron, thinking now of the electron as a little particle, we're not thinking about the quantum condition yet. So if we consider first the electrostatic potential energy, right, which comes about because if we imagine an amount of charge equal to an electron charge, but kind of spread out to infinity. And in order to build that electron, we have to bring that charge in from infinity to this point. That corresponds to this electrostatic potential energy, E squared, the magnitude of the square of the magnitude of charge, or the square of the charge, divided by this radius that we're trying to figure out now. And the relativistic mass energy, mc squared, corresponds to the electron mass. So we equate these two, solve for R, and we get this collection of fundamental constants, the Thomson scattering length for an electron, equal to the classical electron radius. So this was all developed. J.J. Thomson, I think it's John Joseph Thomson, was developing all of this when quantum mechanics was just in its infancy. So also was relativistic theory of relativity. These are notions that come about after the publication of the relativity principles and the basic quantum principles. Okay, and then we consider this question of the phase reversal. Back here, we look at this diagram. The electric vector of the scattered radiation is anti-parallel to the perpendicular component of the acceleration. So perpendicular to this direction of observation, there is some component of this acceleration, and the sense of the electric field vector at that point is opposite that of the perpendicular component of the acceleration. And the length of that perpendicular component is given this way. The acceleration magnitude times the sine of alpha, where alpha is this angle between the direction of observation and the direction of acceleration. Okay, so back here. What does that phase reversal look like in terms of how the scattered radiation relates to the incident radiation? How the scattered wave relates to the incident wave? Well, the acceleration, of course, perfectly follows this force imposed on the electron. So it's an oscillating force going from positive to negative and through zero, and so the acceleration behaves in the same way. So the phase of the acceleration is equal to the phase of the incident wave. I have to also think about, well, what about the position of the charge momentarily, or instantaneously, as it goes through its oscillation? Well, if we, at this point, so the acceleration, the force is maximum, the acceleration is maximum, but the displacement at the top of the crest or at the bottom of a trough is zero. That's the so the electron is coming up, momentarily stops, and then comes down. So the position of the charge, the displacement of the charge from its equilibrium mean position is out of phase. There's a phase difference between it and the acceleration. And so that means that, and this phase difference, as you can see, is pi over 2, 90 degree phase difference. So this is the point at which the electron is moving at its maximum speed, okay? And at the crest here, it's zero speed momentarily. And then the scattered wave, in the same way, we're concerned with, well, what is, as this charge is undergoing this motion, what's the effect on the scattered wave? Okay? So the scattered wave is a further pi over 2 out of phase. Okay? So the net result is that the phase of the scattered wave is pi different, it differs by pi from the phase of the incident wave. So this is just another way of stating what that Thomson diagram says. The Thomson diagram was just considering an acceleration, not necessarily a harmonic oscillation. So it was a point particle, the electron, and given a boost of acceleration, it could be just an instantaneous impulse. But then find the electric field at some distance, some particular point at some distance away from the electron. But now we consider the fact that this is really we're concerned with an oscillatory motion because the acceleration comes from this electric vector oscillation in the incoming radiation. It's the same thing, different color. The other thing that Thomson figured out, in addition to this relationship between the incident and scattered waves, or incident and scattered radiation, is this matter of polarization. So in general, what he was concerned with was unpolarized radiation impacting the electron. That is, the electric vector could be, that's oscillating, could be oscillating along this direction, that direction, this direction. So there'd be a circular arrangement of these electric vectors, changing, of course, with time. So at any particular oscillation, for any particular polarization, here call it E0, we can always decompose it into a pair of perpendicular components, one component perpendicular to the plane of the scattering. So that's the plane in which these three arrowheads, those 3 points define. So they define a plane, that's the plane of scattering. So there's a perpendicular component, and then, well, there are two perpendicular components, a vertical one and a horizontal one. And then in this diagram, we allow for the fact that the phase reverses, going from the Roman E to the script E for the electric component of the scattered wave, electric component of the incident wave. So this is a straight through scattered wave, which of course the scattering in this incident direction is kind of superimposed on the largest part of the incident radiation is not scattered. There's a component in this direction which is scattered. It's straight through scattering. Okay, so then the phase reverses. So E naught and this E naught, script E naught and Roman E naught are opposite directions. And then if we're considering an observation out here along this direction, which is 2 theta away from the incident direction, we have the similar arrangement of the polarization vector components, but we have to adjust for this 2 theta angle. So we have to, in effect, figure out the projection onto the horizontal plane through this angle 2 theta. So we get a correction, in effect, of the y component by amount cosine 2 theta. So there's the result of the polarization. So here's the Pythagorean relation for the square of the x component, the square of the y component, but it modified by the cosine of 2 theta, so that then squared. That gives us the squared component of the resultant. Most of you are going to be, when you're actually doing biological crystallography, you'll be dealing with synchrotron data. Synchrotron data is not circularly polarized, as Thomson considered. Well, there weren't any synchrotrons for him to consider or play with at the time. Eddie will talk with you a lot about, I think, synchrotron physics and its use in crystallography, synchrotron radiation use in crystallography. But because the radiation from a synchrotron comes about because we keep electrons circulating at high speed in a tunnel, but when there's a circular path, a curved path, means an acceleration, right? Because even if the speed doesn't change, the direction changes. So anytime there's an acceleration of a charged particle, there's the emission of electromagnetic radiation, and that's what's going on in a synchrotron. And then it's further boosted by the imposition of oscillating magnetic fields on that circulating beam of electrons to intensify the radiation. But the radiation comes off essentially tangent to that ring, and the ring, of course, defines a plane, so there's a preferred polarization in the radiation coming from a synchrotron, whereas in the radiation coming from the sources that we have upstairs, the rotating anode source or sealed tube source, those are unpolarized X-ray beams that we use for the diffraction experiment. So one needs to make a similar calculation to this one, where we say that X and Y projections, although are different, because it's the radiation coming off tangent to this great circle that is the synchrotron. Okay, so this just points out that whatever direction of polarization we're considering, we can always resolve it into a pair of perpendicular components that are, related in this way. The square root of 2, 1 over the square root of 2, because we're talking about an isosceles triangle in projection here. Okay, and then we did look at these diagrams. So here we have a preferential, this is a linearly polarized incident beam, so we're just considering the straight through beam, also linear, the polarization didn't change. But then in these other directions, of course, the scattering is relatively weaker, so we're showing lower amplitude oscillations, but of the same frequency. And then here's the case for vertical polarization of the incident beam, here for horizontal polarization of the incident beam, and then what would we see in these several different observation directions. And here tries to illustrate the jumble of polarizations in a circularly polarized beam, like the ones we can produce upstairs. And that led us to the notion that these electron oscillations, when the electron is being tickled, impacted by unpolarized radiation, then it undergoes three-dimensional oscillations. And this is a way to think about that. In the one case where all the springs to this center mass are of equal spring constant, equal stiffness, and then we can have, because of peculiarities of the neighborhood that the electron or the particle finds itself in, we might have springs of different stiffness, so we can get then anisotropic elastic constraints here, isotropic. And the classical electron radius. Okay. Just another picture. And a reminder of the Thomson analysis of polarization. And here's another way to look at that. If we consider that we're looking down from above or up from below onto the plane of the scattering, that is the plane determined by the incident beam and this diffracted beam, the so-called equatorial plane of the scattering, what happens to the polarizations? Well, the vertical polarization component, this one, root 2 over 2, stays the same. I'm sorry, the horizontal component, root 2 over 2, stays the same. For the unscattered beam, for the beam scattered to this point, we still have that same horizontal component, and here the same. What's happening to the vertical component, however, well, the unscattered beam, the undeviated beam, has the same vertical component as scattered and incident. But if we're up here at this point of observation, well, the vertical component has been modified by this cosine 2 theta effect, just as we saw on the other kind of more perspective diagram. And then if we're going to yet a higher scattering angle, 2 theta, again, this component is reduced by cosine of 2 theta, but now 2 theta is a larger angle. And when we get to 2 theta of 90 degrees, we're looking at the scattering in direction perpendicular to in this equatorial plane, then the cosine of 2 theta is 0 for 90 degrees, or pi over 2. So the beam that's coming off in this special direction is just polarized in the horizontal direction. So the component of the scattered beams stays the same, perpendicular to the equatorial plane of scattering, but decreases to 0. And then if we continue on, it will increase again if we consider the back scattering direction, back toward the source.
What's the square root of 2 over 2 is coming from the sine of?
Right, so we're considering that we have equal components here, say a y component and a z component. Okay? And if we just consider any, or maybe it's better to show it on the other diagram, this diagram. So we're considering some general direction labeled E0. Okay? So now we want to project that onto the vertical axis and the horizontal axis. Okay? So it goes as we got these, what shall I say? We have these isosceles triangles. Right? It's like the diagonal of a square. Root gives us this root 2 factor. Okay, so having digested all of that, we now consider, well, what about a bound at? We paid all this attention to a free electron, either at rest or move with in uniform motion with a constant non-relativistic velocity. So a free electron, either moving or at rest, but uniformly moving if it's moving. Now we want to consider an electron that is not free, that is bound to an atomic nucleus, which bears a positive charge. Well, again, we have a situation where we have to balance these forces, the Newtonian force expressed as ma, here's the Coulombic force expressed as EQ, and then this thing, Kx, is the elastic force, like a Hooke's law spring. So we have an elastic constant times the displacement of the particle away from its mean or zero position. So we have to equate the Newtonian mechanical force, Newtonian second law force, F equal ma, to this Coulombic force, F equal QE, and modify that by this Hooke's law spring. The nucleus is trying to pull the electron back as it goes through its oscillation. And we can define that Hooke's law constant in terms of the mass of the electron and the natural frequency of its oscillation. That is, if it were set into oscillation and then left alone, it would continue to oscillate with a certain frequency. That's omega naught. Or put it the other way around, the natural frequency of the electron would be given by the square root of this spring stiffness constant, the Hooke's law constant, divided by the mass of the electron. All right, so we say we want to solve this differential equation for x. Well, this differential equation has a solution of the form x equal x naught e to the I omega t. So this e to the I omega t keeps turning up, because remember, every time we differentiate e to the ix, we get e to the ix again. And if it's e to the I ax, then a comes out as a constant in front, so we get a times, as indicated. So the I omega part comes out front, okay? And then again, we just regenerate this function. And then if we wanted to do the second derivative, in order to get the acceleration, that's the second derivative with respect to time. Here, first derivative with respect to time gives the velocity of this motion. Do the second derivative, and we come out again. Out comes another factor, I omega, and then the same function for x naught e to the I omega t. But the product of I omega and I omega is the product I times I is minus 1, omega times omega, omega squared. So this is the acceleration that the electron experiences under the influence of the Coulombic force. So we make those substitutions into the equation of motion. We have this for the Newtonian acceleration. We have this for the Coulombic driving force, the oscillating incident radiation, and we have the restoring force, the restraining force, K times X. Solve for X, bump, 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 bump. This comes down to just 1 over omega squared minus omega naught, with this incident amplitude, the mass, the charge, and then the wave factor, e to the I omega t. So now looking at the scattered wave, again using the Thomson result, the negative of the charge times the acceleration divided by the square of the speed of light and the radius out to the point of observation. So we make those substitutions from what we have developed here, and this comes to give us the scattered wave, whose amplitude, script E naught, is this collection of things outside the factor that involves the frequencies. So the Thomson scattering length for the electron, the amplitude of the incoming radiation, the distance away of our observation point to be looking at this wave coming off, right? So there's the classical electron radiation. Then all of this stuff that precedes the frequencies factor, we symbolize as script E naught. That's that amplitude coefficient for the scatter.
What's the,
Yes.
why are we always choosing E naught or A naught? What is that?
You mean what's the quantity with the subscript 0? Is that what you're asking?
Yeah.
Okay. Well, we know that we take it on faith, and we're not going to go through a course in ordinary differential equations, to say nothing of partial differential equations. But a differential equation of this form, where you've got the second derivative and here first derivative, and here a constant. Okay? So the subscript 0 in all of these places represents an amplitude of these oscillating quantities. Right? So this is the x naught is the amplitude of the displacement oscillation, and its phase is given by e to the I omega t. Okay? So the way we characterize any wave by amplitude and phase.
Okay.
Right? So that happens to the displacement, that happens to the velocity, that happens to the acceleration as well. So when we write without the subscript 0, we're thinking about the wave, amplitude and phase. When we write it with the zeros, we say, okay, here we're just considering the incoming amplitude, and here we're just considering the outgoing amplitude. Okay, so this is an electron in an atom. And the atom could be moving around. The atom could be at rest. Of course, atoms never are. And it could be moving with a uniform, it could be in uniform motion, non-relativistic velocity. So there's, again, a classical physics result. Now we come to considering the complication of the fact that when an electron is set into this oscillatory motion that involves that acceleration A, well, an accelerated charge emits electromagnetic radiation. So this oscillating charge is kind of losing energy. That's like that motion, that oscillating motion is damped. And the damping, typically, if you consider, for example, the mass on a spring, the example of, classical example of damping, consider the mass on a spring. Okay, you set it in motion. It gets oscillating at its natural frequency and so on. But suppose you do this with the spring or the mass in a column of water. Right? So the frictional effect of the mass moving up and down in this column of water is going to be this equivalent to this radiation loss damping. And in the case of the mass on the spring, the damping effect is proportional to the velocity, the instantaneous velocity of the moving mass. So we have the driving force, which is the electrical one. We have the Hooke's law restoring force, which is the effect of the nucleus wanting to restrain the motion of this oscillating electron. And then we get this radiation loss damping force, which is proportional to the first derivative. So here we have another differential equation. Second derivative, a constant, the displacement, the function, and then its first derivative. So the function, its first derivative, second derivative, and its driving force. Well, when we solve that equation, we end up with, okay, it has a solution e to the I x naught e to the I omega t, okay, just as the earlier one did. But now when we solve for the several effects, well, here's the frequency of the radiation. Here's the natural oscillation frequency of the dipole oscillator. And in comes this imaginary term, because this is the first derivative of the displacement. We take the first derivative of x, okay? Well, what do we get? Well, we get that factor out front, x naught. Then we get omega t, I omega, so x naught I omega times e to the I omega t. Okay? So when we do the second derivative, we get this result, which is, as we shall view, I squared times omega squared. But in the case of looking at just the first derivative of this function, maybe I should have written them out more explicitly. But anyhow, in the first derivative, there is a survival of this imaginary unit. Right? X naught I omega times e to the I omega t. That would be the first derivative of this function. So that I omega survives as a result of the damping, a consequence of the damping that goes on. The damping goes on because the accelerating charge emits electromagnetic radiation. So the net result is for the amplitude of the scattered wave, given by the Thomson formula, we get then this frequency factor, has the radiation frequency in the numerator and denominator. It has the natural oscillation frequency of the nucleus electron dipole, and it has this imaginary correction term that appears because of the radiation loss damping. So the net result is that the scattering factor for an electron in an atom is equal to this amplitude of the bound, corresponding to the bound electron, that is this amplitude here, and the amplitude of the free electron. Well, what was the amplitude of the free electron? It was just this part, the Thomson scattering length, but with negative sign, right, because of the opposite, the antiparallel acceleration and electric field vector. So the scattering factor for an electron in an atom is the ratio of these two amplitudes, the amplitude of the, due to the radiation in the bound state compared to that of a free electron. And that just comes down to this frequency factor, omega square over omega square minus omega naught square minus I gamma omega. And gamma is this, when we introduce this damping term, we define the kind of stiffness for the damping term as the mass times this quantity gamma. So gamma is equal to the ratio of this damping coefficient to the mass, in our case of an electron. So then we can just divide out by omega squared here. We get 1 over 1 minus the ratio of the two frequencies, the natural frequency, the radiation frequency, and this imaginary term. This correction for the damping. Radiation loss for the damping.
What is gamma?
Gamma is just a symbol we introduced to define this, this damping factor, kappa, in a way analogous to the definition we gave to the elastic force constant. So it's in the case of the elastic force constant, it's the mass times the natural frequency. Gamma is just a coefficient. We can say it's just a coefficient. Gamma is equal to kappa over n. And kappa is a constant. It depends on the intensity of this oscillation, how much radiation is being emitted, again, according to the Thomson formula for the scattering.
So the gamma itself is not a constant, right?
Yes, gamma is a constant.
Gamma is a constant.
Right. It's different for the different electrons in a given atom. Okay, it's not the same for each electron, but for any one electron, there is a gamma. Right? Or for any one electron, there is a kappa. Okay, so we have this is the general result, this ratio of scattered amplitude from the atom, the electron in the atom, the scattered amplitude from a free electron, this frequency. And if we divide out, we get this more simplified form. Well, not more simplified, alternative form. Problem, we still have the imaginary unit in the denominator. Typically, we like to have it in the numerator, and in the notes that are on the website, so the expressions get a little hairier looking because you have to multiply numerator and denominator by the complex conjugate of the denominator. Then up in the numerator would be the imaginary unit along with some other factors, and in the denominator, the imaginary unit would have gone away because the imaginary unit, the conjugate, is opposite sign, algebraic sign. So this just restates the same equations with the labels as given, and gamma is, this constant for any given electron is generally much smaller than the radiation frequency, which remember now is something almost 20 attohertz for 1 angstrom wavelength X-rays. So it's a very high frequency. Gamma is a constant much smaller than that. And so that means that we can neglect the I gamma term to a fair approximation when gamma is small compared with the radiation frequency. Then we're just left with this ratio of the square of the ratio of the frequencies, but the damping effect then is negligible in such a case. If the natural frequency is near the radiation frequency, then what happens? This ratio goes to almost 1, and we're just left with a unit value for the electron scattering factor. Did I say just put it the other way around? If the radiation frequency is greater than the natural frequency, we're left with just unity, because this guy in the denominator would swamp this guy in the numerator, and so this would evaluate to a very small number, almost 0, close to 0. So for a free electron at rest, the scattering factor of the electron is unity. For undamped oscillation of the electron under an electron bound to a nucleus, we get this scattering factor for that electron, and in the high frequency limit, this goes to approximately unity. So now let's look at those same relationships in terms of a diagram. So the diffraction condition that we're always concerned with is that we have this unit vector, S naught hat, divided by lambda. So we divide by the wavelength in order to get a unit length direction vector. And we have here a situation where we've got this incoming radiation with this wavelength lambda, and lambda is going to be something on the order of the distance from the nucleus to an electron of interest. Right? So considering an electron that is something on the order of 1 wavelength away from the nucleus. So we're still worried about just the scattering by this single electron, not the scattering by the nucleus. We just have this trace out to say, this is what would be the case for an electron at the nucleus. So the nucleus just defines an origin and a direction for this incident, these incident and scattered waves. Okay, so S naught plus the scattering, right, gives us, the scattered vector plus the scattering gives us the incident vector, right? So this, the negative of this, brings us to here. We call this the scattering vector, the angle between incident beam and the scatter vector is 2 theta. So if we just do a little bit of algebra with those guys, we say that this vector plus this vector gives us the reverse of this vector. We can always, not the reverse, we can always move the tail of a vector to a different origin, right? So this guy here, the scattered vector here, is equivalent to this direction at the top of the diagram. So the incident plus the scattering vector gives us the scattered vector. And the length of these S naughts, since we define them as unit vectors, right, they're each of length 1. The dot product of the two of them is this cosine of the angle between them, 2 theta. The scattering vector is the difference between them divided by the wavelength. Okay? And the scattering vector is just another expression of the Bragg law, or involves another expression of the Bragg law. Okay? So if we were considering these two different possible paths for scattering, the difference between them would be the distance of the electron from the nucleus dotted into the difference between those two direction vectors. So, okay, a diagram for scattering of X-rays by an electron in an atom. I also want to consider the case of the scattering of the totality of electrons in the atom. Okay? So we know these days that we consider the electron distribution to be like a cloud centered on the nucleus. Okay? So now we're considering two little pieces of the electron cloud, little volume elements in the electron density distribution for a many electron atom. Okay? So we have the incident wave vectors and then the scattered ones. And we want to consider, well, how do the phases of these two pieces of the scattering compare? So again, we're considering wavelengths of the order of an atomic radius or of the atomic diameter. That's what Kreskotka. And consider the difference between these two path lengths. So scattering by this volume element adds a component x1 to the total distance, and the scattering by this one subtracts a component x2. So the difference between the lengths of these two different paths for scattering from two different points in the electron density distribution is this, call this distance delta x change. The change from is the difference between x1 and x2. The extra path here, and then the extra path here. So that the difference in path lengths translates to a difference in phase, right? So we may be looking here in a direction where the scattering is very weak. These two could interfere. The waves from these 2 points could interfere destructively or constructively. We could be looking at a strong scattered beam here or a weak scattered beam, depending on direction, depending on the difference in the path lengths. Here's an illustration of the same kind of thing, but we're just worried about scattering from an incident beam two points that are on that same direction vector. So we have scattering from this point, we'll call it R0. A scattering from this point, we'll call it R1. Okay. The difference in the lengths of those two, here we drop a perpendicular to get the difference in length, that produces a change in phase. We're talking delta R instead of delta X, it's different like this. But we get this phase difference between these two scattered guys. So they're rather out of phase here. Okay? They're almost, it looks like almost 90 degrees out of phase in this particular diagram for this particular distance between the 2 points.
What
Yes?
Why are we using the K there? Is that supposed to be?
Oh, okay, sorry. Yeah, K is the, this gets confused with the elastic force constant that we were talking about. This is a different one. This is the so-called wave vector, which is the reciprocal of the wavelength scaled by 2 pi. Sorry. This is, for any wave, we define a wave vector, conventionally symbolized K, as 2 pi over lambda. An obvious point of confusion, but use both symbols so often, it gets ingrained in your head, which is which. Okay, but the point is that the scattering from different points in the atomic electron density distribution, these scattered beams or scattered waves from the 2 different points can interfere destructively or constructively. And I think that's illustrated here too. So we're considering now an atom represented by the circle. We're considering 2 points in the atomic electron density distribution, A and B. So in this case, both of them sitting on the incident beam direction. And so we drop perpendiculars from each of those points to the other beamlet, right? And then consider what happened as we increase the scattering angle. So this is the straight through scattering. Here's scattering at some angle 2 theta. And here's scattering at some even larger angle 2 theta. So then, because of this variation, the AB distance, which considering the same 2 points in this electron density distribution, the A point and the B point don't move, but as we change the angle at which we're viewing the scattering from those points, there will be a change in the degrees of interference, all right? And the higher the angle, the better the chances for interference because of different path lengths to and from the points of interest. And now you have to consider this kind of happening at every point in the electron density cloud. So the greater the scattering angle, 2 theta, the greater the difference between the wave path lengths. Okay, these waves coming out here, we finally note them at a faraway detector as a point, right? The fact that there's a small difference in their direction is immaterial when we're looking at things from far enough away. So even similarly here. Okay, the greater the scattering angle, 2 theta, the greater the difference between the wave path lengths, and then therefore the greater the destructive wave interference because of the variation in the wave path length, and then the greater the scattering factor fall off, the greater the decrease in scattering factor with scattering angle. And the net effect of these things, when one works it out in a more consistent total way, is that you get scattering factor curves that look like this. So here is this is scattering angle, but represented as sine theta over lambda rather than 2 theta. This is a convention that was adopted early on in the analysis of X-ray diffraction. But the point to be made here is that the scattering power of an atom, right, the scattering factor, little f, for atom A, is approximately proportional to the atomic number of atom A. So here, we just look along the vertical axis for the moment. Okay, so the scattering factor for the hydrogen atom cuts the vertical axis at 0.1, cuts the vertical axis at 1 unit, 1 electron, call it. Say we're counting electrons here with respect to the atomic numbers of the atoms. Okay? And then these curves, we just plot half of them, okay, because it's the same on the other side. So what the in total, these scattering factor curves are going to roughly look like the shape of a Gaussian function, look like a normal distribution, kind of look like the so-called bell-shaped curve. But that's an approximation. They differ from one atom to the next because of the different electron populations in the various orbitals of the atom. So here's a carbon atom coming in at 6, at 0 scattering, oxygen at 8, chlorine up here at 17. The calcium ion, right? Take away 2 electrons from a calcium atom, you've got the same kind of total electron number as in a chloride ion, where an electron has been added to a chloride ion. These are these 2 species, chloride minus and calcium double plus, are isoelectrons. Here's iron coming in at 26, I think. Right? So it's stripped of 2 electrons. This is a ferrous ion. Here's a bromide ion at something like 31 electrons. So this is just a sampling of atomic scattering factor curves. And they all bear the fact that the scattering falls off with increasing scattering angle because of those interference effects from different parts, scattering from different points in the electron cloud. So here's a composite showing for a bunch of elements. I think here this plots everything up to uranium. And you can see that the shapes of these curves vary slightly, but still the rough shape, if you had to describe it, would be approximately Gaussian.
Those calculated or measured?
The measurements are tricky, and especially the early ones were difficult. So these are calculated on the basis of an electron picture for these atoms. So these are results from quantum chemical calculations in both of these diagrams. So these are calculated. And there are different, of course, different models for atomic electron density distribution. That gives very slightly different atomic scattering factor. So what the kinds of things that happen in these squiggles is illustrated here in a simple case where we're looking at just this curve has this little hump. So that's the curve for z equals 6, and down here below it the curve for z equals 4. Why does that hump occur? It's a peculiarity of the electron distribution in different atoms. So if we consider the beryllium atom, which has z equals 4, then its electron configuration is 1s squared, 2s squared. So in the second shell, the L-valence shell, that's filled. That's the maximum, 2 electrons in an s orbital. And for a carbon atom with atomic number 6, the valence shell, so there's 1s2 that's inside here, and then it's 2s2, 2p2. So that means that these 4 electrons half fill the L-valence shell, because we could have 2s2 and 2p6. So we've got a total of 8 electrons can be accommodated in the L shell, and we've got half that number for a neutral carbon atom. So there's a special effect on atomic electron density distributions when these quantum shells are either full or half filled. So, and what it means is that when the valence shell is half filled, there's a slight expansion of the volume of the electron cloud for those outer or valence electrons, and therefore a contraction in reciprocal space of the low angle scattering factors. So what we remember, what we're plotting here in all the cases of these scattering factor plots is sine theta over lambda. Okay? Sine theta over lambda is the way we write scattering angle conventionally. But if we expand the atom, and so the dimensions here of sine theta over lambda are what? Reciprocal distance, reciprocal angstroms. Okay? So this is the behavior of these scattering functions in reciprocal space. But what we're talking about here is the behavior of the atomic volume in real space. So an expansion of the atom leads to a contraction of the scattering factor. And since, well, we'll see in a minute. So there's another way to plot the same thing, not as convenient a way, but a way to plot things so that you get a kind of an impression for what's going on as in the scattering, various scattering directions around a given atom. So at the center here of these plots, we consider we have the atomic nucleus. Here for a neutral carbon atom, here, and here for a sodium ion, singly positive sodium ion here. And now we're considering, okay, what's the scattering, how does the scattering factor vary as we go away from the zero scattering angle? So here we scatter to this direction 2 theta, this direction 2 theta, this direction 2 theta, and so on. So as we increase the scattering angle, the length of these scattering factor vectors is decreasing. Okay? Same here. The difference between these two is that in this one, we're introducing a smearing factor. That because this is a carbon atom at rest, no motion. Here's a carbon atom that's jiggling around because of thermal vibration, kind of like Brownian motion, right? But so that smears out the electron density distribution. Here you can see it's a little more shaped, and it's got this narrowing and so on. Here less. So this is a smeared carbon atom with a small vibration amplitude. And here, this is the case for a sodium atom, a sodium ion, also at rest. So considering the change in the scattering power with scattering direction. Again, that variation occurs because of the interference effects among wavelets coming from different parts of the different points in the distribution. The other thing we can talk about these scattering factors, again, against sine theta over lambda, this is a reciprocal space variation, is that we can dissect it in terms of core and valence electrons. So what do we have for a carbon atom? Carbon atom has, in the K shell, 2 electrons. So its electron configuration is 1s squared in this shell. In the L shell, we have 4 electrons, 2s squared, 2p2. Okay? Those are the valence electrons. This is where the chemistry occurs between carbon atoms and other carbon atoms, or whatever carbon is interacting with. Oh, okay. So we'll stop with this, I guess. So here's this dissection. Notice that the inner shell, okay, that's more compact in direct space. 1s2 distribution of electrons is more compact than the 2s2, 2p2. Okay? So the K shell scattering doesn't fall off as quickly as the L shell scattering. Okay? So here we have a broader electron density distribution and therefore a narrower scattering factor. So here's the total for a carbon atom with atomic number 6. So there are 4 L shell electrons which are out there in the periphery of the atom, and there are 2 K shell electrons which are tucked in close to the nucleus, and their scattering, the core scattering, persists longer. By the time we get beyond about 0.5 sine theta over lambda, the valence shell scattering is all but gone. Okay? These guys, these valence shell electrons, in such a case, will have little effect on the intensity of the scattering. They don't contribute much, hardly anything. Okay, let's wind up with this. So if we just go now into atomic space, into real space, angstrom space, atomic radius, and plot the electron, the radial electron distribution in the various quantum shells of, in this case, a potassium ion. Okay? So it's got the argon core, and then we have the configuration is 1s2, 2s2, 2p6, 3s2, 3p6. So it's got argon, it's got an inert gas, or noble gas electron configuration. And so it's like an electron distribution in an argon atom, but of course the nuclear charge is there. So the 1s electrons have a radial distribution which peaks very close to the nucleus. The 2s have a distribution that peaks further away, the 3s further away, and similarly the 2p and the 3p. So this is just going out a radius of an atom, out to a distance of 2 angstroms. Okay? So, for potassium ion. And corresponding then to those components of the electron density distribution, we can calculate the corresponding components of the atomic scattering factor. Okay? So here is the one that falls off very little is the K shell. That's due to the 1s electron. So that's a component of the scattering factor coming from the K shell electron. And then we get the effects from the L shell electrons. They're falling off in the S electron's case more gradually and more steeply in the P electron's case. And then we can go to the next shell, the M shell, the third principal fiber. So here, reciprocal space, here, direct space, or crystal space, or atom space. And so those guys, those scattering factor components, to get the scattering factor of the potassium ion, we have to just sum them point by point along the sine theta over lambda axis. So when we add up, say, at this point, there's a contribution of this much, and then a contribution of this much, and then added onto that a contribution of that much, and then added onto that a contribution of that much, and so we build up the total scattering factor curve for the potassium ion. And we do this only to a relatively, we're not going out the whole electron. But notice what persists, what's happening here. All of the valence electrons, all of the 2p and 3p electron scattering factors from those electrons, they're falling rather steeply, but we still have this persistent inner core which continues to scatter. Right? So we can still, even at high scattering angles, still see density due to the innermost electrons, high angle scattering for the innermost electrons of the potassium ion. Okay, we'll talk about these functional forms more next week.